Hey, AP Calc BC. Today is a big day. We are officially starting Unit 4. So up on the screen right now, I have our overview of all of our units for the year. You'll only have access to these folders as we get to lessons within these units. So right now, you kind of only have up through Unit 3, which is what we just finished. And you'll notice that the folders change colors to orange after this unit, so starting with Unit 4. And there's a reason for that, because everything we've done so far was all AB material, and right now we're officially starting the BC material, or the C in the BC, you could say. So we're starting with parametric, polars, and vectors. You'll see that our units for the rest of the year include advanced integration techniques, series convergence, power series, Taylor series, and error, and advanced differential equations. So we're going to get to all of this mostly in second and third marking periods before we then switch back to AP exam review and we kind of put all the pieces together. So I'm going to go into Unit 4 here, and if we take a look at the overview, let's read this together. Students will build on their understanding of straight line motion to solve problems in which particles are moving along curves in the plane. So we're taking straight line motion, which is what we usually think of as being on one axis, right? If you might have like an x-axis and there is a particle that's moving along the line. But what if that particle could move along a curve in the plane instead? That's where this comes into play. Students will define parametric equations and vector-valued functions to describe planar motion and apply calculus to solve motion problems. So planar motion, meaning that the particle can move anywhere in the plane, not just in a straight line. And we're going to learn two kind of types of functions that will allow us to do this: parametric equations and vector-valued functions. And these are very similar. They're interrelated. But it's going to change the way that we view how you can graph a curve on the XY axis. We're not adding a Z axis. We're not switching to three-dimensional space, but we are adding an extra variable. And you'll see exactly what I mean in just a minute. Later in the unit, we're also going to learn about polar equations, and these are a special case of parametric equations that will apply calculus to analyze graphs and determine lengths and areas. So this unit's going to be a lot of graphing, a lot of still deriving and integrating, but with motion on a coordinate plane. All right. So that's the overview. Specifically today, we're just going to see an intro of graphing parametric equations. So in College Board's version of this course, which is, the official version, we're in Unit 9. So we're going to be doing all of Unit 9 in our Unit 4. And we're going to start with Lesson 1, which is defining and differentiating parametric equations. Specifically in our lesson today, we're just going to be defining parametric equations. So we're going to stick with methods for calculating derivatives of real value functions can be extended to parametric functions. All of this kind of includes the derivative. We're actually not going to quite get to that today. We're going to stick with just what is a parametric equation in the first place. All right, so that's our goal. With that being said, I'm going to switch over to the notes. We're going to do one question, and then I'm going to show and I'm going to show another screen to kind of hopefully help this make sense. I'll show an analogy. All right, so let me pause this so we can get over to the notes. All right, so here we go. Lesson 4.1, graphing parametric equations. For these examples, all of these examples today, we're going to make a table of values and sketch the curve indicating the direction of your graph, then eliminate the parameter. So there's a lot going on here. First of all, we need to know what a parameter is. A parameter is, in this case, an independent variable that both x and y depend on. So we're used to having x as the independent variable and y as the dependent. So in other words, when you think about how your graphing calculator graphs your curve or graphs your function, it slides along the x-axis, and whatever x value you're at, it plots the y value based off of the equation, right? That's what we're used to. But this is going to work a little bit differently. We have this external variable t that doesn't even show up on the graph, but t is the independent variable, and x and y depend on t. So when we graph this, there's kind of an extra variable working in the background. So what we need to think about here is that this together is one parametric equation. It's split into two partial equations, right? It's two equations that together make up a parametric equation. So to graph this, what we're going to do is we are going to plug in certain t values and see what the x and the y are. So I'm telling you, if we look at this first equation, and this is kind of getting ahead of ourselves here, but what we're going to try to do is make a table of values with t, x, and y. And the t is then going to kind of go away when we graph. You'll see. But the first thing I'm going to think about is what t values can I plug into both of these equations. And in this first one, we noticed that we can't plug in anything lower than 1, or else it won't be able to take a square root. So that's just, the point of that was just to show that I'm going to start with 1 for my t's, okay? And what I need to do is find the x and the y value for each t. So I'm going to plug 1 in here, we'll get 0. If I plug 1 in here, we'll get 3. If I plug 2 in here, we get 1. Plug 2 in here, we get 4. Plug 3 in, we'll get root 2 and 5. Plug 4 in, and we'll get root 3 and 6. Plug 5 in, we'll get 2 and 7. So you can think of t as like time if you want, and it's as time goes by, we have a certain x and a certain y value. So let's plot the x and the y values on our coordinate plane and see what it looks like. So we've got 0, 3, 1, 4, root 2, 5, okay. 2, 7 is another nice one. 1, 2, 3, 4, 5, 6, 7. And then in between there, we have a 5 and a 6. So it's going to look something like that by the time you sketch it. Okay, and so our curve is clearly going up like this. And it's going to keep going because think about, like, we could keep plugging in more t's. And we get more points that are in that direction. However, it stops here. We can't plug in anything smaller than 1 for t, so we're not going to have more to do in that direction. Typically, for a parametric equation, it's normal to see like an arrow on your curve indicating which direction the curve is being drawn. So as t's are increasing, since the t itself doesn't show up on the graph, we know it started here and was going this direction. So we're going to put an arrow symbol like that to show that it's going that way. All right, so you can see now that although the t was necessary to even come up with the x and the y values, the x and the y worked together to create one graph without the t's even being visible. So there were two equations, but it comes together to only have one graph. So the directions also said, okay, we indicated the direction on the graph, and then we have to eliminate the parameter. So we're going to see what do we get for an equation that's something that we normally see with just x's and y's. So we're going to start with the x equation. And we're going to use what you are familiar with from your algebra skills, we're going to use a substitution method to get rid of the t. So I'm going to solve this for t equals. So I'm going to end up with x squared equals t minus 1, x squared plus 1 equals t. And I'm going to use that to plug in for t in the y equation. So we have y equals t plus 2. So y is going to equal x squared plus 1 plus 2. Or in other words, x squared plus 3. However, if you look at the graph, we don't have the entire function x squared plus 3. That would have a whole other half over here, and it's cut off. And that issue arose all the way back up here when we said that the square root cancels out if we square both sides, right? There was no plus or minus right here. It's just positive. So because of that, our solution is kind of including values that aren't actually real. So the domain has to be limited to 0 to infinity, or you could say x is greater than or equal to 0. That's kind of a more common way that we might see this. Okay, but that is the xy version of the parametric equation. Now the t was eliminated, so now we don't have our time or we don't have our direction included anymore. It's just the same graph, but it doesn't have the direction or speed or anything like that. But you can think of this still as like a particle motion. It's as time goes by, the particle is moving to these points along this curve, but the curve itself can also be expressed with this equation. So that's a parametric equation. We have 2 more questions to do that will just kind of continue to introduce us to more ideas that go into this, but I'm going to pause real quick to show you an analogy. Okay, so here's our analogy. Maybe this looks familiar to you. Maybe you had one of these when you were younger. It's an Etch-a-Sketch, right? And what happens with an Etch-a-Sketch is that you can spin these dials at the bottom here to kind of draw something on the screen, right? And the one dial controls kind of the horizontal lever and moves it up or down. And the other dial controls a vertical lever and moves it left or right, kind of behind the screen. And when you kind of scroll the dials together, you can move all around and like this, make diagonals, you can cross each other, whatever you want to do. Now, since I'm using an electronic version here, I can't actually show you that I'm spinning the dials, but I think you can probably imagine what's going on here. So for a parametric equation, I want you to think of the person who is spinning the dials is kind of acting as the T. They're the external force that's controlling the X and the Y dials. And that kind of leads into the next part. One dial is the X equation and the other dial is the Y equation. So the X controls, like the X value of the order pair, the Y controls the Y value of the order pair, and the T is the person who's controlling both of them. And if you think about this viewing window here as kind of like your graphing calculator, the graphing calculator always sketches an XY graph from left to right, sketching the Y value and then for each X value, right? As X increases, it sketches each Y value from left to right. But parametric graphs don't necessarily get graphed that way. They don't have to act as functions, right? As functions that meet the vertical line test. They can cross each other because it doesn't necessarily matter that the X just has to go from least to greatest. The T can control and make it go kind of all over the place. So you can see it can cross over itself without any major issues. I mean, it looks kind of wacko, but this is totally doable with parametric equations when we have the external independent variable T that's controlling the X and the Y, okay? So that's how this Etch-a-Sketch relates to parametrics. And with that being said, We're going to switch back to the notes and try B and C. All right, let's take a look here at letter B. You can see that we once again have two equations. We have x equals t squared minus 3, y equals 2t. So the x and the y both depend on the t variable. And this time we have limitations on our t. T has to go from -2 to 3. So what I'm going to do is make my chart with t, x, and y. And to graph this, we are just going to put all of the integers from -2 to 3 as our t's. And so I'm going to plug each one of those in for x and each one of those in for y, and I'm going to write down the values that I get. All right, that's what I got here. And let's graph this before we get too much further. So we're going to have x's and y's to graph. I'm just going to assume that each of these lines represents 1. So let's see, we got 1, -4, and then -2, -2, -3, 0, -2, 2, 1, 4, and 6, 6. All right, and because our t was limited, specifically from -2 to 3, we're not going to extend past these points at all. So it's just going to look like this. And that's the whole thing. And from -2 to 3, we started here and went this way. So we're going to put an arrow somewhere along this curve to show that that's the direction that we're moving in. And our next step is to eliminate the parameter. So we're going to eliminate the t. So I'm going to start with y this time because the x one looks a little bit more complicated. So t equals 1/2 y. So we plug that in for t in the x. So we have x equals 1/2 y squared minus 3. And if we square that, we get 1/4 y squared minus 3. And so that's valid. The directions didn't say that our formula had to be solved for y equals. So that's going to be kind of the most helpful version of this. And you can see it is a sideways parabola. So it makes sense. The only other thing I would say is that we need to have limitations. And in this case, it's going to be best if we make the limitations in terms of the y, because the x's kind of stop here and here, so they stop in different places. So if we think in terms of the y-axis, we're going to go from 1, 2, 3, from -4 to 1, 2, 3, 4, 5, 6. Like this. So that's the limitations. This time we're putting limitations on the range, but it still works, okay? So this time you can see that even though we had a t variable, it didn't show up on the graph, and our graph doesn't pass the vertical line test. So this is not a function. And normally we would not be able to have this as one y equals equation, right? It would have to have a plus or minus if we solve this for y equals. But when we have it as two equations serving as one parametric equation, both individually are functions, but together they form a graph that is not a function. It doesn't pass the vertical line test. But again, think of this as particle motion. So as time is -2, there's a particle sitting at 1, -4. And then as time goes by, it's moving along this curve until it gets to here. That's what's going on here, okay? We got one more to look at, and this one has some trig. We've got sine and cosine involved. So for this one, we have x equals 3 plus 2 cosine t, y equals -1 plus 3 sine of t. And I'm trying to think about what t values are going to make this easiest. And I'm telling you right now, we're going to want t's that end up nicely on the unit circle. So I'm going to start with 0 and then go to pi over 2 and then go to pi to 3 pi over 2 and to 2 pi. And if we plug these in for the x equation, you're going to end up with 5, 3, 1, 3, 5. And for the y equation, you're going to end up with -1, 2, -1, -4, -1. Okay, and then on the graph, we plot these points. So we have 5, 1, 2, 3, 4, 5, -1, 3, 2, 1, -1, 3, -4, and then 5, -1 again. And so we've got these points in like a diamond shape here. So the question is, how do we connect the dots? And the hint here is that, remember, sine and cosine come from the, a circular origin, right? They're representing the unit circle, or at least that's how we can evaluate them. So this is actually going to be making a circular pattern. In this case, it's more of an ellipse. So it looks like this. And it actually just restarts after 2 pi, as you might expect, just like the unit circle does. So we can put our arrow this direction, because that's the direction that we formed our dots. But you could prove this if we plugged in a whole bunch more t values in between the ones that we plotted. But I believe that our graphing calculator can also plot this. So I'm going to pause for just a second so I can set up the calculator properly, and then I'll show you what I did. Okay, so here's what you can do. You can go to mode on a graphing calculator, and if you go to where it says function, if you change it to parametric, as you might expect, this makes our calculator in parametric mode. So it allows us to graph parametric equations. So if you go to y equals, now for each equation that you can enter, it's split into 2 parts. It's x1 and y1 in terms of t. That's what the little t means. So I plugged in 3 plus 2 cosine t and -1 plus 3 sine of t. To enter the t, you just have to press the button that we usually press for x right here next to alpha. If you look at the bottom of the screen where my finger is, that button always says x, comma t, comma theta, comma n. This is the mode where it means t. So you can just press that button and it makes a t form instead of an x. So you type this in, take a look at the graph, and you can see it made it into a circular shape. It looks like an actual circle, but that's just because our axes are not evenly spread in the x and the y direction. So if I make it a square, I think that's what fixes it. Yeah. Z square makes it so that the x and the y distances match, and then you can see this is more of an oval or an ellipse. But anyway, it also sketched it in the same direction that it should have been sketched according to our data with our table and our graph. We also need to eliminate the parameter in this question. So let's start out with the x equation. And start to solve this for t. So it's going to become x minus 3 equals 2 cosine of t. We'll divide by 2. And we are not quite solved for t yet. The easiest way to write this, since there's an x over here, is to say that the cosine inverse of x minus 3 over 2 equals t. So then if we substitute that into the y, we'll get y equals -1 plus 3 sine of the cosine inverse of x minus 3 over 2. So that's technically a valid solution, but we can go further, and this is probably the trickiest thing that we'll see. Well, this is definitely the trickiest thing that we'll see today. is just to remember from pre-calc, how do you simplify this? And it's all about remembering what these trig functions really mean. It's saying here that the sine of some angle is what we want to plug in here as our answer. And it's the sine of an angle that has a cosine, that is x minus 3 over 2. So we're looking for the angle that has a cosine, that's x minus 3 over 2. And then what's the sine of that angle? It's going to be easiest if we draw a right triangle and think about SOHCAHTOA. So here's my rough sketch. And I'm going to have some angle theta. So think about that. Theta is represented by this. So if theta equals the cosine inverse of x minus 3 over 2, that's saying that the cosine of theta is x minus 3 over 2. And the easiest way to think of that is think about SOHCAHTOA. Cosine is adjacent over hypotenuse. So in my version of this right triangle, I'm going to make the adjacent x minus 3 and the hypotenuse 2. Okay. So then what's happening here is we want the sine of that angle, right? That is representing theta. So now we're saying, okay, what's the sine of this angle? So the sine, remember, is the SO in the SOHCAHTOA. So it's the opposite over the hypotenuse. Think about a squared plus b squared equals c squared. And it would be the square root of 4 minus x minus 3 squared. Okay, so that's the opposite. So opposite over hypotenuse is going to be the sine. So the sine of this angle, it can be expressed as the square root of 4 minus parentheses x minus 3 squared all over 2. So I'm going to rewrite this. 3 times the square root of 4 minus x minus 3 squared all over 2, because that's the opposite over hypotenuse. And you could rewrite this probably to make it look a little nicer by moving the over 2 out in front. And we could keep going. We could kind of FOIL this and then combine like terms inside of the square root. But this is already a much nicer version of the answer. And if you type this into your calculator, you will see that it already starts to graph part of that ellipse. Okay, so that's what's going on there. So that is a brief introduction to graphing parametric equations. It's not all that different from what you would normally do. We just have this extra variable t that goes away once you graph, except for the remnant, that is this arrow that tells you which direction the t went in. Okay, so that's how you do that. Excuse me. As always, let me know if you have questions with the homework, and I hope you have a great day. Thanks for watching.